All right, working from version 2. That's the one I handed to you, I believe. Yeah, version 2. All right. Oh, let's see. Oh, we're starting at the top. Number 1. For the reaction of sodium bromide and chlorine gas to form sodium chloride and bromine, the appropriate pass reactions are oxidation reduction reactions. So sodium bromide with chlorine gas. And this will be an aqueous solution. And bromine gas to make sodium chloride and excuse me. For the reaction of sodium bromide with chlorine gas to form sodium chloride and bromine. Chlorine. Oh. There we go. And then we get sodium chloride and bromine. And bromine should be a liquid, right? At room temperature. Isn't that one of the, yeah, bromine's a liquid. Okay, which is not important for this, but we want to split it into oxidation and reduction steps. So in order to do that, we need to know the oxidation states for each of the elements. Bromine's -1, sodium's +1. Okay. Elements are 0. That's 0, that's 0. This is -1, this is +1. Okay, so the oxidation step, remember, oil rig, oxidation is loss. Which one lost electrons? And if we go from, nothing happened to sodium. Sodium is a spectator. But chlorine actually gained. Bromine lost. Right. I like to use tie lines. This is a loss of 1 electron per bromine. Okay. And chlorine gained 1 electron per chlorine. It went from 0 to -1. So let's balance the equation while we're here. Why don't we? Right, we need 2 chlorines. We need 2 bromines. So that means times 2 equals 2 electrons, and times 2 equals 2 electrons. Whenever you have an oxidation and reduction, they always occur together. And one step has to transfer exactly the same number of electrons as the other step. So now that we've got this balanced equation, the oxidation step, oxidation is loss. So we're looking at, and based upon the answers, they want only the ions. All right. So these are going to be 2 sodiums and 2 bromine ions in solution. So we have 2 bromines. And that leads to this bromine. Okay, but how about the electrons? If you lose electrons, they show up on the product side. Right? Okay, so far? Okay. Now for the chlorines, we have this chlorine gas yields that chlorine ion. There are 2 of them. And this is the gain, the reduction step. So we have 2 electrons here. Right. So that gives us the oxidation and reduction steps. And it looks like the oxidation step is this one. Yep. Reduction step is this one. Yep, and that would be B. B would be the answer. Have you tried some of the review problems?
This.
Yeah. No? Okay, so
Go away for you.
this is all new. So this is how we deal with an oxidation reduction. We split them out as separate steps. Right? Oxidation is loss, reduction is gain. That's also how we balance equations too. Okay. I'm not going to be using this one. Can you erase it? Switch to a different marker. These Expo markers work great on fresh boards. But if the board's just the least bit porous, it's a pain. So let me get one of these. These guys are more forgiving. 2. Ammonium metavanadate reacts with sulfur dioxide in acidic solution as follows. The ratio of X to Y. So we're going to balance the equation. Right?
We've done that before, haven't we? Balance equation.
We balanced equations, but we haven't used the oxidation reduction method.
You have to do that for these.
Yeah, there's an abbreviated form and then there's the long way. I'm going to see if we can, this says in acidic solution, which means that we're probably looking at the long way, right? VO3 minus, that's the vanadate ion. Ammonium is a spectator. That's why you don't see ammonium here in that expression. SO2 and yields VO2 plus and SO42 minus. Okay, but we're looking for the coefficients for each one of these. All right, and the way we work this is you have to decide, you have to break this out into oxidation and reduction steps. So you need to know the oxidation numbers for each of the elements. Oxygen is given. Oxygen is -2, -2, -2, -2. So now we can deduce what vanadium is. Remember, the total of the oxidation states has to equal the charge on the ion, if there is a charge. So with 3 times a -2, you have a -6 oxidation states that have to be balanced by the cation side. But we need to keep one of those negatives out for the charge. That means you really only have to balance the -5. So this is a +5. Okay? All right. Here's a -2 times 2 is -4. This is a neutral. SO2 is neutral. So we have to balance all 4 of those with a +4 on the sulfur. Okay? And we do the same thing over here for vanadium. -2 times 1 is minus. Okay. You've got a -2 for the oxygen, but you have to end up with a +2. So how do you do that? A +4 for that vanadium. And this -2 gives you a 2+ charge. Okay. And this one is a -2 for the oxygen times 4 is -8, but we're going to hold 2 of those out. So this is a +6. All right. These are the oxidation states for the sulfur and vanadium. So I'm going to clean it up a little bit. Right. We don't need that anymore. We don't need that anymore. We don't need this one anymore. That one. This one. There we go. Okay, now we can split it out for the oxidation and reduction steps. Okay, oxidation step. Oxidation is loss. Which one lost electrons? It went more positive. Sulfur? Sulfur went from +4 to +6. That's oxidized. So we have SO2. I'm gonna put this +4 here just to keep a reminder. And that went to SO4, 2 minus, and this is +6. Okay, that's the oxidation step. Reduction step is the vanadium. It went from +5 to +4.
Loses during oxidation. Like,
Oxidation is loss. Oh, it lost electrons.
oh,
If you lose a negative, it makes it more positive.
Okay.
Right? Okay. Yeah, it takes a little practice to get that intuition. And then we've got the vanadium over here, VO 2 plus. This one is +4. Okay. So the next thing you do, according to the rules, is you balance everything but oxygens and hydrogens. So we've got one sulfur here, one sulfur there, we're good. One vanadium here, one vanadium here, we're good. Then you balance the oxygens with water. So we've got 2 oxygens on this side and 4 on that side. That means we need 2 more oxygens on this side. Right? Okay, so we're going to add them in as water. There's our 2 oxygens. On this side, we have 1 oxygen here and 3 there. So we need 2 more on this side. Okay. Now we balance the hydrogens as protons in acidic solution. So what we've got here is 4 hydrogens. There's our 4 hydrogens. Okay. We've got 4 hydrogens here. There's our 4 hydrogens. Okay. Now you balance the electrons. How many electrons were transferred? In oxidation step, when you oxidize, you lose electrons. They always show up on the product side. So if we went from a +4 to a +6, we had 2 electrons that had to be lost there in order to make that +6. So -2 and a +6 is a +4. On this side, we're reducing. So we have to add electrons. We went from a +5 to a +4, which means we just add 1. Right, +5 to +4. Yeah, just add 1. Okay, now, before we can put them back together, we have to balance the electrons because electron transfer for oxidation has to be exactly the same number as reduction. So we've got 2 electrons here and 1 there. That means this has to be 2. We've got the ratios here fixed for this step. So anything you multiply it by, you have to multiply by the whole thing. So we need 2 more here. That makes this one 8, this one 2, this one 2, and this one 4. So we use that multiplier. Now that we've got the electrons the same, we can add it back together. Right. Electrons are going to cancel. 2 waters and 4 waters. That means these 2 waters are canceled, and these are back to 2. Okay. Now we can add them together, I think. Oh, hydrogen, excuse me. 4 hydrogens on this side. We had 8 on this side, so we're back to 4 there. So now we've got, let's see, we've got 2 VO3 minus, and then we've got SO2 plus SO2, and then we've got 4 hydrogens. Okay. See, that's 1, 2, 3. Okay, that's good. On this side, we have 2 VO 2 plus and SO4 2 minus, and then we got 2 waters. 1, 2, 3. Okay. So to answer the question, let's see. The ratio of X to Y. X is this one, and Y is this one. X is this one, Y is this one. Ratio is 2 to 1. Right. That's why the answer is C. Okay. I was just running through the procedure for balancing equations using a redox method. Now, this is an acidic solution, right? And remember, unless we've created a battery where we separate these two out into separate containers and then link them together to make a circuit, then all of this is happening in the same solution. You just put it together, those hydrogen ions are everywhere. So that's an acidic solution. If we wanted to make it basic, it didn't say basic, but if we wanted to, then you have to neutralize all of these hydrogens with hydroxyl. So if we were to go basic, you would just add 4 hydroxyls on both sides. Right? That would make what? 4 waters over here. Correct? So 4 waters there and 2 waters here means those waters are gone and these are 2. So now the equation would be that one, 2 waters here, and then that one, and 4 hydroxyls on that side. That would be a basic solution. I mean, that wasn't the question, but I figured since we had it up here, I'd go ahead and do it. Okay. 3. Let's scroll, we get 3 and 4 at the same time. The following reaction occurs in aqueous acid solution. In the balanced equation, the coefficient of water is. So this is another one. Right. Nitrate plus iodide. Excuse me, yields iodate ion plus nitrogen dioxide. All right, so the process is the same. You got to figure out which one is oxidation and which one is reduction. Right? When you have a single element ion, that's the oxidation number for that ion. Oxygen's always -2, unless it's in a peroxide. If it's a peroxide, then the oxygens are -1. Okay. So if this is -2, total -4, that's a +4 for that nitrogen. There we got a -2 for that oxygen times 3 is -6. We're going to keep one of those negatives for the charge. That means we only have to neutralize 5 of them. Okay. That one's done. This one's a -2 times 3 is a -6. -5, that's a +5.
Where you kept the negative.
Yeah. I have to hold out one of those negatives because I don't want to neutralize it. I got to keep that charge. So count up all the oxidation numbers. Right? -2 times 3 is a -6, right? And iodine is a +5. That's equal -1. There you are. You have to end up with the charge on the polyatomics. Okay, so we got that done. Got that. This is no charge, so I'm going to move that. Remove those. Okay, now we're ready to split them out. Oxidation step. Which one increased the oxidation number? Put it that way. Which one lost electrons? Increase the oxidation number, -1 to +5. That's an increase. So we have I minus to IO3 minus, this is +5, and this is -1. Okay, reduction step. Which one did the oxidation number decrease? We added electrons to it. +5 to +4. NO3 minus went to NO2. Okay, so now we got one iodine, one iodine, that's good. One nitrogen, that's good. That will balance the oxygens. We have 3 oxygens over here. 3 waters. I'm going to go ahead and do the hydrogens while we're here. 6 hydrogens were added on that side, so we have 6 hydrogens on this side. Okay, we have 3 oxygens and 2 oxygens. I need 1 more over here. And then I need 2 hydrogens over here to balance. Now we can do the electrons. Oxidation step. I need electrons over here. How many? Minus to a +5. We lost 1 to go to 0, and we lost 5 more to go to +5, so that's 6. 6 electrons were lost. If we go from +5 to +4, that means we only had to gain 1. Okay? All right, now we need to reconcile the electrons. If we multiply this whole thing by 6, we got 6 there, 6 here, 6 there, 12 there, and 6 there. Now we can add them together. Let's see, we get rid of the electrons, they cancel. Waters, we got 6 waters there and 3 here. So this one's out, and this one becomes 3. Hydrogens, we got 6 hydrogens here and 12 there. So we get rid of those hydrogens. Now this becomes 6. Okay, what was the question? Coefficient of water. So we don't have to bring it down because those waters are gone and we have 3 waters left over. So the answer is C, 3. Coefficient of water is 3. Okay? Takes practice to get comfortable with it. There's some equations, you know, when we first learned how to balance equations, we used that budget method. And the budget method works for a lot of equations. It's very efficient. But there's some, especially these where you transfer electrons, it's almost impossible to balance it without doing it this way. And sometimes you combine both of them. All right, you do a redox a redox approach. You finish it off with the budget method. Okay, number 4. The following reaction occurs in basic solution. Okay, this is the one where we do need to transfer. I use what I call a fake acid method. You go the acid route first, and then you neutralize the acid, and that gets you to the basic. So we got fluorine, excuse me, water, oxygen, and fluoride ion, right? Okay, This is 0, -2, +1. Oh, by the way, did you notice in the discussion, water is always +1 when it's first in the, well, actually it doesn't have to be first, but it's +1 in most cases. When is it a -1? It's a -1 when you combine it with a metal. For instance, aluminum hydride. In that case, aluminum has to be +3. So this means that one's -1. But all the other times, hydrogen can be taken as +1. Okay, that one's 0 and that one's a -1. So we need oxidation and reduction steps. Let's see, oxidation is loss. Who lost electrons? Oxygen. It went from a -2 to a 0. So we've got water with the -2 here, goes to oxygen with 0. Okay, so that means the reduction has to be fluorine. With a 0, it went to there. Okay, this has nothing but oxygen and hydrogen. This one has 2 fluorines, so we'll put a 2 here. Now the fluorines are balanced. We've got 2 oxygens here, 1 here. So if we do that, that'll give us 2 oxygens over there. Right. Like that. Okay, now we can do the electrons. Oxidation, we need electrons over here. How many? Well, we went from a -2 to a 0. So we lost 2 times 2. We lost 2 for every oxygen, but there are 2 oxygens. So it's 4 electrons. Okay. On this one, we gained electrons. How many? Well, 1 for fluorine, but we got 2 fluorines. Okay. So some of the coefficients, so we got to bring it down. All right. Wait a minute. Not yet. 2 electrons, 4 electrons. Thought I was going to miss it, didn't you? 2 there, 4 there, 4 there. Okay, now we can bring it down. Electrons are out. Yields O2 plus 4. Let's, yeah, 4 fluorides plus 4 hydrogens. There we go. Okay, and this is in basic solution. So what we have to do is neutralize those hydrogens. And they also show up over here, hydroxyls. Okay, this produces 4 waters. Right? HOH, H2O, 4 waters. And we got 2 waters over here already. Those guys are gone, and this becomes 2. So some of the coefficients: 2, 6, 7, 11, 13. Okay. Next. That's some repetition there. Move down to this one. Did we do this one before? No, it didn't have iron in it. It was something else. Okay, never mind. So the appropriate half reactions. This, it looks like it's balanced already. 2Fe2 plus chlorine yields.
Is that from number three?
I'm sorry?
I think that's from number three.
Yeah,
Or that bounce.
right. One of the Roman numerals will be the oxidation step and the other one will be the reduction step. Yeah. Fe3 plus, E3 plus, and 2 chlorides. Okay, so that's 0, that's -1, that's 3 plus, 2 plus. This is going to be the oxidation step. Right? It loses an electron to go to here. So we would say Fe2 plus, 2 Fe3 plus how many electrons? Well, 1 for each, but there are 2. That's the oxidation step. I don't think we're finished with it though. Because, right, you got a 2, 2, and 2. So we would reduce it by dividing the whole thing through by 2. And plus 1 electron. Then the reduction step would be chlorine yields Cl minus, and this is reduction, so we have to add 1 electron each, or 2 electrons. So this is the reduction step. Okay, so the reduction step would be Roman numeral 1, right? Roman numeral 1. And the oxidation step would be, have to be 4, right? Yeah, 4. All right, so 1 and 4, A. Okay, number 8. How many electrons are transferred in the following reaction? All right, 2 chlorates, number 8. 2 chlorate ions plus, and I assume this is balanced because it's got hydrogens in it and 10 iodides yields 5 iodines plus chlorine plus 6 water. Yeah, that's already balanced. Okay, so we've got to figure out who does what. All right, this is -2 times 3 is -6. Hold 1 out. This is a +5 for chlorine. And iodine is that -1 charge. This one's 0. This one's 0. And the oxygens didn't change and the hydrogens didn't change, so water is just there. So we don't have to contend with that. So what we have to do is figure how many electrons actually moved. All right, if we go from +5 to 0, that's loss of 5 electrons for each chlorine. Per chlorine. But we have 2 chlorines, don't we? Equals 10 electrons. Now that would answer the question, but I want to be sure. So if we go from here to here, that's a gain, loss. Wait a minute. Oh, no. That's a gain. I go to +5 and 0, right? Gain 5 electrons. This is a loss of 1 electron per iodine, and there are 10 of them. Equals 10 electrons. There we go. So this is the reduction step, and this is the oxidation step. 10 electrons moved. E is the answer. Okay. All right. Let's see, who's next? 11. Consider a galvanic cell based on the reaction Fe2 plus and dichromate minus yields Fe3 and yes, chromium 3 plus. Okay. In acidic solution, calculate the voltage of the standard cell carrying out this reaction. All right. It's possible that we could do this without doing the whole equation, but these equations are funny, right? When you look at the standard reduction potentials in that table at the very end, right down somewhere. I think I missed it. Standard reduction potentials, no. No, keep going. Nope, more. Here we go. Notice that these guys have hydrogens and water and all that stuff together. So, and they're very specific, the voltages required. So that tells me that we do need to produce the half cell reactions. So that means we got to split them up. That's 2 plus. This one's minus 2 times 7 is minus 14. We're going to hold 2 of them out. So we balance plus that with a plus 12, but we got 2 of these. So each one of the chromiums is plus 6. And the rest of them are charges. Okay, now let's split them out. Oxidation reduction. Let's see. Iron goes to here. It's oxidized. It lost 1 electron. 2 plus, iron, 3 plus. Okay. This one has to be the reduction then. Cr2O7 2 minus, and that's a plus 6 here. Goes to Cr3 plus. So we got the same number of irons, that's good. 2 chromiums there, we need 2 chromiums there. Now we don't have to balance oxygens here. 7 oxygens there. 7 waters plus 14 hydrogens. Now we do electrons. This one lost an electron. Okay. This one gained 3 electrons per chromium times 2. 6 electrons. So now we need to multiply this one by 6, 6, 6. Okay. Okay. So now we need to reference, this is in acidic solution. Yes. Now we need to go down to our half reactions. Keep going a little bit more. There we go. And find our half reactions. Fe2 plus to Fe3 plus. So let's see. If there's a 2 plus, now it goes to 3 plus. No, that's not it. So it's very specific. Let's go back on this side. Look for iron. No, it must be over here somewhere. I missed it. Another table? No? Should be here. Show me where it is. I did it right, didn't I? Yeah. Right. There it is. Okay, 0.77. But this is backwards. 0.77. So standard potential, 0.77. It's flipped. So that's a minus. All right, we're going the wrong direction. Now we have to flip it because it's oxidation. These are standard reduction potentials. Okay? Standard reduction potentials. And the reduction then, we can read it as is. We need dichromate to Cr3. So dichromate to Cr3, 7 waters, 14. Yeah, that's it right there. 1.33. All right, so 7 from 13 is 6, right? Yeah, and 7 from 12 is 5. 0.56 volts. 11. I got a bad feeling about this. Oh, there it is. D. 0.56 volts. Now, this is standard voltage. All right, it doesn't take into account any differences in concentrations. If we change the concentrations from the standard, by the way, what is the standard? Concentration of 1 mole, 1 molar. So that would be 1 molar, 1 molar, 1 molar, 1 molar, 1 molar, and water is a solution, so it doesn't matter. That's the standard reduction potential, the standard potential for the cell. In order to calculate the actual voltage for the cell, we have to use the Nernst equation to take advantage of changes in concentration. But this is the standard potential. And the standard potential, it doesn't matter what these values are. Right? If you look up the reduction potential for Fe2, Fe3 plus to Fe2 plus, and it says one of these, one of those, one of those, then the fact that we've had to multiply 6 times each one to get to add them together doesn't matter. It's still the same standard reduction potential. Okay? That value only changes when we incorporate concentrations. And we probably got an example down here somewhere. Okay, a strip of copper is placed in a 1 molar solution of copper nitrate. It's number 14. Okay, strip of copper is placed in 1 molar copper nitrate, a strip of silver, 1 molar silver nitrate. The 2 metal strips are connected to a voltmeter by wires, and a salt bridge connects the solutions. The following standard reduction potentials apply. Okay, which of the following statements is false? Okay, what they're giving you there are the 2 half cells for this reaction, but they're giving them to you in reduction potential. So silver plus an electron yields silver metal. All right, that's the first one. And it's a plus 0.8 volts. 0.80 volts. The second one is copper 2 plus 2 electrons yields copper metal. And that half cell voltage is 0.34. All right. So how do we make a battery out of this one? Remember, a galvanic cell runs spontaneously when you calculate the positive voltage. All right, so how would we make this positive? These are both reductions. One of them's got to be oxidation. So that means you have to flip it. And that changes the sign. So the way you do that is you say, what happens if you flip this one? Negative 0.8 and 0.34, that gives you a negative number, doesn't it? So we flip the other one. If we flip the other one, going back that way, then this becomes negative. And the overall voltage now is subtract that from this one. 6 and 3 from 7 is 4. So that's the way it would be if this were the oxidation step and this were the reduction step, right? And our terminology says reduction always occurs at the cathode. Oxidation occurs at the anode. So when you draw your cells, your half cells, and I can't remember which should be which. I think the cathode's always on the right. So we've got electrons flowing here, and the cathode would have the electrons exiting on this side. And then they would be entering here to be an oxidation. So that means the anode would be over here. This would be the copper. That would be copper right there. This would be silver right here. And then you'd have your solutions. You'd also have a salt bridge. Okay, that would complete the circuit. All right, now let's look at the questions. Which one's false? Electrons flow in the external circuit from the copper electrode to the silver electrode. Yep. From copper to silver, they're going this way. A is true. The B, the silver electrode increases in mass as the cell operates. Right. I mean, if you add electrons to the silver in solution, it deposits silver on the electrode. So that silver electrode is going to increase in mass as the cell operates. B is true. C, there's a net general movement of silver ions through the salt bridge to the copper half cell. That doesn't happen. The salt bridge is set up so that you can't get any bulk movement of either one of these ions through the salt bridge. What moves are the ions that you place in the salt bridge. All right, so if we remove negatives over here, say we have potassium chloride in our salt bridge. Okay. The chloride ions are going to move over here to replace the lost negative charge from the electrons. And the positive potassium ions are going to move over here to accommodate the loss of positive silver ions that are now plated on the electrode. So potassium moves this way, chloride moves that way. But the copper and the silver ions don't move. So C is the false one. C, that does not happen. And you can assume that since we found the right one, that D and E are both true also. All right. That was 14. Let's see, we can get 16 on there too. 15. Which of the following species cannot function as an oxidizing agent? Okay. Oxidizing agent. So what is the oxidizing agent? It's the one that is reduced. Right? Oxidizing agent is the one that is reduced. So in order to be reduced, it has to accept electrons. Which one can or cannot accept electrons? Well, if we've got sulfur solid, yeah, we can make an ion out of it. Right? We can add electrons to that. So it works. That's A, B, C, D, E. So what's B? B is nitrate, NO3, NO3 minus. So what's the oxidation state for nitrogen? We have -2, -6, -5 left over, we have +5. Yeah, you can go from +5 to -5. Right, so nitrogen can be reduced further. How about C? Dichromate. We've already seen that one. This was +6 and it went to 3+, didn't it? So that one can be reduced. It's an oxidizing agent. Iodide. Can iodine accept more electrons? No. That's maxed out. Why? Because with one extra electron on iodine, it has met its octet. It has a full, right? Look where iodine is. If it gets an extra electron, it looks like xenon is happy. So you're not going to add any more electrons to that one. So D is the one that cannot function as an oxidizing agent. It will not be reduced further. Okay, 16. Let's see. Which metal, aluminum or nickel, could reduce zinc 2+ to zinc if placed in a zinc solution? Okay. So we got zinc 2+. These are reduction potentials. Zinc 2+ plus 2 electrons yields zinc metal. And its standard potential is -0.76, -0.76 volts. The next one, aluminum, Al3+ plus 3 electrons yields aluminum metal. And its reduction potential is 1.66. And then nickel, 2+ plus 2 electrons yields -2, nickel, excuse me. And then -0.23 volts. Okay. In order for aluminum or nickel to reduce zinc to zinc metal, this has to be as written. We're trying to make zinc out of this. So this is the cathode. So one of these, we have to make both of them into anodes. If we go backwards, like that, one of them would be an anode. That would make this plus and this plus. So the way to answer this question is, which one's spontaneous? Put these two together right here. Right? If we put these two together, we would have 0.9 plus 0.9 volts. Right? Aluminum would do it. Nickel, right? Nickel and these two would give you a negative 0.53 volts. That's not spontaneous using nickel. Right. So the only one that would work is aluminum. Okay. Right, 16, 17. All right, consider the galvanic cell shown below. Contents of each half cell are written beneath each compartment. All right. What's the E0 for this cell? That one's easy. If you're going for the E0, you look at the voltages for each of the half cells and flip one of them so that the summation is a positive number. Okay, so if we have chromium plus 3 electrons, let's see, this is, I got the number now, 17. So if we have chromium 3 plus 3 electrons yields chromium metal, that would give us negative 0.727. Negative 0.727 volts. That's standard potential. Hold on. Okay. I'd check myself. It is asking for the standard potential, so we don't have to consider the concentrations. The concentrations would be going to the Nernst equation where we have to calculate Q. Okay, and the other one is bromine plus 2 electrons yields 2Br minus, and that potential is plus 1.090 volts. Okay, it looks like if they wrote it in standard terminology, the chromium side should be the cathode, right? Reduction. And this one should be flipped to make the anode, but that won't work. So that cell is written backwards. In order to make this a positive outcome, which one needs to be flipped? That one. That one has to become positive. We make this one, we add them together. If we say flip this one, that makes it more negative. So if we flip this one, that becomes positive. And now we have 7, 11, 8, 1, 1.8 volts. 1.817. So the answer to that one is A. Okay. Now, let's see, this is a different cell. What's the value of easy? Oh, I guess we're going to do this one too. All right. That's number 18. All right, with these two cells, if we're only looking for the standard potential, the concentrations don't matter. So what we need to do, since they're both written as reduction potentials, one of them has to be flipped. We got to make an anode out of one of them. So which one would we flip and still give us a positive summation? The second one, right? The chromium. Flip the chromium. That means we have 1.506 volts and negative 1.330 volts for the chromium. 6710. Right, so that's 0.176 volts. It should be C. Yeah. Okay. Now your book, I think, says calculate the voltage of your cell, take the, reduction potential for the cathode and subtract the potential for the anode. And that's what we're doing here. We just flip the reduction equation to make an anode out of it, and that changes the sign, then we add them together. So you're ending up in the same place. But with my method, I think you understand why, rather than just memorizing the formula. Yeah. Question?
Yeah. What about 21?
21. Is that the same? Yeah, it's the same one. What is the stoichiometric coefficient of hydrogen ions? Okay, well, that's where we do what we did before. Right, we've got the half reactions there. We have to make them match. Right. And we'll do that. And I think well, I'll skip temporarily. I'll go back. I was looking ahead to see if some of these, we need to keep some of these and just do them out of sequence rather than have to rewrite them every time. Yeah, not this one. We just did 19, didn't we? We did 18. Okay, 19. When current is allowed to flow, which species is reduced? All right, so let's go ahead and write those up. Because 19, 20, 21, it looks like we're using the same galvanic cell, just asking different questions about it. So the anode is going to be where oxidation occurs. Right? And oxidation is the one we flipped. Right? That would be the chromium. So that's going to be 2 chromium 2 Cr3 plus, right? Because I flipped the equation, plus 7 water yields dichromate ion and 14 hydrogens. Yes. Plus 6 electrons. Okay, and the cathode is going to be the one as written as a reduction potential. The manganate ion plus 8 hydrogens plus 5 electrons yields Mn2 plus and 4 waters. Okay, now this voltage here is going to be 1.506, 1.506, and this one's going to be negative 1.330, negative 1.330. Standard potentials. Okay. Now, what's the question? When current is allowed to flow, which species is reduced? Well, reduction occurs at the cathode, right? If this is the cathode, then MnO4 minus is reduced. So the answer should be C. Yes. Okay? Okay. 20, we use the same equations. What is the value of Q, the reaction quotient for this cell reaction? In order to calculate Q, we have to have the stoichiometric equation for the whole thing. So this is now going to be 20. All right, so we can't put these together yet because that's 5 electrons and that's 6 electrons. So how do you get those electrons matched up? 5 in one and 6 in the other, cross multiply. Take that 5 times this one. And take the 6 times that one. Okay, that means this is 10. This is 5 times 7 is 35. This is 5. What's 5 times 14? 70. Yep. And this is 30. Okay. This one is 6. We used that up there. This is 48. This is 30. This is 6. No. And this is 24. I already did that one, didn't I? Yeah. And we use this. Now we can add them together. So the electrons, for the purposes of stoichiometry, the electrons cancel. We're going to need the number of electrons, though, for the Nernst equation. So we'll bring it down, let's say, let's do this one first. 10 Cr3 plus, and then 6 MnO4 minus, and then 35 waters. 35 waters, 48 hydrogens. And then over here we have, let's see, we do the chromiums first. Cr2O7 minus plus 6 Mn2 plus do the waters next, 24 water and 70 hydrogens. Now, water's 35 here and 24 there. So all these waters go out. And 24 from this is 11, right? 11 waters. Hydrogens, we have 70 hydrogens there and 48 on this side. So 48 from 70 is 2 and 4, 2, 22. So we have 22 hydrogens. Okay, there's our balanced equation. Now, in order to calculate Q, we need Cr2O7, 2 minus, to what power? To the 5th power. Then we have manganese 2 plus to the 6th power. And then we have hydrogens to the 22nd power. That's in the numerator. Denominator. Actually, that would be K. I'm using square brackets. I need to use parentheses. We need Cr3 plus to the 10th power. We need MnO4 minus to the 6th power. And we need, well, water's pure liquid, it doesn't count. Right, so that's it. Okay, now we can calculate, we can put in our values. What's the dichromate concentration? 0.3 molar. 0.3 molar to the 5th power. What's the manganese Mn2 plus concentration? It's 0.2 molar to the 6th power. What's the hydrogen ion concentration? That's good. They're both the same on each side. So it's 0.01 molar. 0.01 molar to the 22nd power. And then divide by chromium 3 plus concentration, 0.4 molar. 0.4 to the 10th power. This is getting ridiculous. MnO4 minus 0.1, 0.1 to the 6th power. So 5, 6, 22, 10, 6. Okay. Now we can calculate Q. All right, 0.3. Enter that one. Then 0.2 and 6 power. Multiply those together. 0.01 and 22 power. What's that? Okay, now 0.4 to the 10th power. Divide that one. And 0.1 to the 6th power. Divide that one. Okay, I get 1.4, two significant figures. 1.5 times 10 to the minus 41. Is that in there? Feel like I dodged a bullet. There are lots of places in here to get lost. Okay, so that takes care of that one. We're going to need that value, so I'm going to leave it there for a subsequent calculation. Let's see, for the same cell in 21, what's the coefficient of hydrogen? H plus. H plus. Oh, here it is. H plus 22. Right, 22. D. Okay, that was 21. We just did 21 for the hydrogen. And 22, they're going to have us, what is the cell potential at 25 degrees as read on the digital voltmeter? All right, here's where we use the Nernst equation. At 25 degrees. Now, in the lecture, I think I derived, or I don't remember if I derived the Nernst equation or if I just modify it for 25 degrees. But let's go down. It's in useful information. Let's see. 22, wasn't it? Nernst equation. Right. Down here somewhere. There it is right there. Okay, yeah, I've only put the one in here that's modified for 25 degrees. Right. So the Nernst equation says the actual voltage, the electrical potential, is the standard potential minus 0.0591 divided by N, and N is the number of electrons transferred, times the log of Q. Okay? So what's the standard potential? We did that one before. I erased it though. So it's 1.506 minus 1.330. Is 0.176. 0.176 is the standard potential. Then we have 0.0591 divided by the number of electrons transferred. Where are they? Here, 30. 30 electrons transferred. And then the log of Q, which is 1.5 times 10 to the minus 4. And that'll give you the actual voltmeter reading, the potential for that cell as constructed. Let's see, I'm gonna do the log first. It's already, let's see, 1.5. Is that right? Yeah, 1.5 exponent negative 41. Take the log of it, times 0.0591 divided by 30, and then subtract that from, see, that's a negative number, so I have to change the sign. 0.176. So I get 0.256. There we go. So let's go back up to number 22. Oops, too far. One per page, it looks like. There. And that says E. Well, rounded off, 0.26. All right. And we're going to skip a few. I assume we're not going to need that anymore. That's why I put them all together. I hope so, because I don't want to have to write this out again. If I do, I'll go to my cheat sheet. That. Number 30. The following has a potential of 0.92 volts. So mercury 2 plus hydrogen yields 2 hydrogens plus mercury 2, mercury subscript 2 plus. So that's mercury 1. 2 plus mercury ends up mercury 1. If the concentrations of the ions were 1 molar and the pressure of hydrogen is 1 atmosphere, then E0 for the half reaction would be. Oh, just look it up. No, it's given to us. Right? Yeah, that is the way the half cells, the half reactions are determined against the standard hydrogen electrode. So notice that hydrogen goes from a 0 to a +1. It is oxidized. It's the anode. That's why the reduction potentials are listed the way they are. They're based upon the hydrogen standard electrode, which is always 1 atmosphere pressure. So if the potential for this cell is 0.92, then the half reaction for that cell is 0.92. The trick question. Okay. I guess we got a lot of repetitive stuff in here, skipping down. Okay. 44. An excess of finely divided iron is stirred up in a solution that contains copper 2 plus ions. So we're putting iron and copper 2 plus ions in aqueous solution. System is allowed to come to equilibrium. Okay. So it probably produces some like that in copper solid. I'm not sure what this would be. A 2 plus, probably a 2 plus. I'm speculating. The solid materials are filtered off and the electrodes of solid copper and solid iron are inserted into the remaining solution. So we're at equilibrium. Right? We've got the forward and reverse reactions are now balanced. And we're going to take that solution and insert the electrodes into it. And what potential develops between the 2 electrodes? That's another trick question. It's at equilibrium. Nothing happens. Right? When you're at equilibrium, you get no voltage at all. That's why in that previous example, we used Q. Q is not at equilibrium. If we use K, we'd end up with 0 volts. So as written, that problem gives us 0 volts. The magic word there is equilibrium. All the rest of it is blue smoke blown in your face to try to confuse you. 49. You make a cell with aluminum electrode in a solution of aluminum nitrate and a zinc electrode and zinc nitrate. If you could increase the concentration of aluminum 3+, which of the following is true about the cell potential? All right, so if we've got aluminum and aluminum nitrate. So let's write this as a,
Is this one like you gotta work it out, like kind of longish?
no. Mm-mm. No, what we need to do is identify which one's the anode, and which one's the cathode.
Gonna run to the bathroom.
Oh, okay, sure. Yeah. Aluminum electrode. Oops, sorry, too far.
Oh, yeah.
Yeah, it's A. 0 volts. No, it should, whatever it's 0 volts, right? It's at equilibrium. So we got aluminum electrode in a solution of aluminum nitrate. So aluminum nitrate is a spectator. So what we've actually got is a 3+ plus some electrons goes to aluminum like that. So we have 3 electrons there. That would be the reduction. So we have a standard reduction potential for that. And the other one is zinc and zinc nitrate. So zinc in zinc nitrate would leave us with zinc solid. And I think zinc nitrate should be, is it 2? Yeah, zinc is always 2+. It's one of those, it's always 2+. So we need 2 electrons here. Okay, now we need the values, standard potential for each one. All right, so we have to go down to our reduction potential table. We need those values.
Let me give it to you.
Oh, yeah, sure.
It's
Aluminum,
aluminum 3+. 8. 2+. 1 and say 7.
no, wait a minute. What's the standard potential for each one?
If this is, give me a bring it up there.
Yeah, okay.
Is it?
Oh.
This one and that one, that's standard route, because you already got.
49. What is it asking me? What's the question asking?
And this says use under standard conditions.
Yeah.
She's asking.
Oh, okay. I need the standard potential first. So aluminum is -166, zinc is -76. 6676.
What does that mean under standard condition then?
1 molar concentration of that ion, 1 molar concentration of that ion is standard conditions. Okay, that's the information I needed. Now let's go back to the problem.
So E will decrease as aluminum increase.
Hold on a second. Here we go. If you could increase the concentration of aluminum, which of the following is true about the cell potential? All right. We may have to combine these. It's a good thing it took me a while to get this far. All right, how are we going to write this equation so it's spontaneous? If we make this one positive, then the sum is negative. So we have to make this one positive. That means it's reversed. This is the anode. This is the cathode. Okay, so if we flip them and match the electrons, because there's no oxygens and there's no hydrogens in here. So if we multiply this one times 2 and multiply this one times 3, we have 2 here, we have 6, 2. This one would be 3 and 6 and 3. Then this one has been flipped, so we've got 2 aluminums over here. Right? And we've got 3 zincs, 2 plus. And then this one goes on this side, 2 aluminum, 3 plus. And then this zinc stays over here, 3 zinc. Then the standard potential for this one would be 0.9, yeah, 0.9 volts, standard potential. So the question is, if you increase the concentration of aluminum, this one, increase that concentration. All right, the reasoning here is, what impact would it have on the cell potential? I mean, would it be higher than this or lower than that? Let's look at the Q. All right, if we do the Q, then we've only got this one and that one, right? These solids don't count. So we got aluminum on top at squared, and we've got zinc on the bottom. Let's see, aluminum 3 plus and zinc 2 plus on the bottom, cubed. And the Nernst equation says that the actual voltage equals the standard voltage minus 0.0591 over N times the log of Q. Okay, so how many electrons were transferred? 6, right? So this becomes 6. This becomes 0.90. So what would happen to the Q if we did what? Increase the concentration. If we increase this concentration, the Q would get bigger, right? It would get larger. Wouldn't it? Right? If we increase the aluminum concentration, the Q would get bigger. So if the Q is bigger, the log of Q would also be larger. We increase the value of Q, we increase the negative, so the voltage would decrease. Okay, see the logic? You want me to go over it again? We had to put the equations together. That's what we did here. So that we could write the Q. The Q puts aluminum on top. Right? And all it says is, what would happen to the cell potential if you increase the aluminum? Effectively, it would drive the reaction backwards. Right? Which would reduce the voltage because you're running the reaction in reverse.
But it becomes increasingly more negative.
Yeah,
I thought you said it makes the cube larger.
it does. And if the Q is larger, if the Q is large, increases the value of Q, then the log of Q is also increased. And that would increase this negative value. Right? If this gets bigger, then the whole term gets bigger. That makes this more negative, which reduces the overall value of the potential. Right? If that negative gets bigger, this whole thing gets smaller. Right? Don't agree with me just because you have to.
Okay, so E will decrease as Q increases.
Yes, that's true. As Q gets bigger, E gets smaller. Yeah, that's exactly right. Now, if we increase the zinc, it'd be the other way around. Q would get smaller. and E would increase. Okay? All right. That was some heavy thinking there. Make your brain hurt. That was 49. Okay, let's see who's next. 56. Okay, how many moles of electrons are produced from a current of 14.4 amps in 3.2 hours? All right. This is a dimensional analysis problem. We have to understand first, what do we mean by amps? Right. An amp, 1 amp is 1 coulomb of charge per second. Okay, so we have 14.4 amps, 14.4 coulombs per second. How many seconds is this thing operating? 3.2 hours. Hours. So we got to convert that to seconds, don't we? We need seconds up here. We need hours down here. How many seconds in an hour? 60 times 60. 3,600. Yeah. 3,600. Okay. So this will give us the number of coulombs. But now we got to convert that to moles of electrons. And there's a conversion factor for that also. It's in your useful information. 14.4 times 3.2 times 3,600. So that's 1.66 times 10 to the 5th coulombs. So what's the conversion factor? You got it there? I'll go look at it. Useful information. It's Faraday's number. Let's see. There it is right there. Right here. 96,485 coulombs per mole. What? 485 coulombs per mole. So we divide that value by 96,485. And that's 1.72 moles. Moles of electrons. All right, so let me go back up. What amount? 56. There it is. 1.72? Yep. That's how many moles of electrons are transferred in that amount of time with that current. That is a huge current too. You don't want that current flowing through your body. It will stop your heart in a New York second. No. No, those were all blank. I mean, unhighlighted. So 64. These are the kind of currents that you'll see in electrolysis problems, where you're plating metals onto other substrates. 64. Okay. What mass of chromium could be deposited by electrolysis of an aqueous solution of Cr2SO4 for 145 minutes using a constant current of 11 amps? Okay, mass of chromium. What we need to find out, all right, here's what's going to happen. The sulfate is a spectator. What you've got is chromium 3+. All right, if we take this compound, Cr2SO4 3, that tells you the charge on chromium. because this one's 2 minus, this one's 3 plus. So what we have is 3 plus yields chromium metal. That means 3 electrons for each mole. 3 moles of electron for each mole of chromium. So what we need to do is find out how many moles of electrons are being used in this process. Right? We have 11 amps. Is it 0.0? Yeah, 0.0 amps, which is coulombs per second. And we've got 145 minutes. 145 minutes. Let's see. Hold on a second. $145, but we want to convert those minutes to seconds. Right, seconds up here, minutes down here. 60 seconds in a minute. There you go. That gets rid of minutes. Now we got seconds. Cancel those. So now this tells us the total charge that transferred in coulombs. Okay. Now we want to convert coulombs to moles of electrons. That's for every mole, we have 96,485. Is that right? Coulombs per mole. Did I get that number right? Well, let's go look. Useful information. Oops, not far enough. In there. 96,485 coulombs per mole. That's right. So that cancels coulombs. That gives us moles of electrons. Now we can convert moles of electrons to moles of chromium. Right? For every 3 moles of electrons, you get 1 mole of chromium. Okay? That gets rid of that one, that one, that one. Now we're up to moles of chromium. Moles of chromium, grams of chromium. Grams per mole is molar mass, right? So I'm close. So let me just scroll up a little bit and get chromium. There's chromium. There it is. 5196, 52.0. 52.00. There we go. That gives us the answer. How many grams? Let me go back to 64. There we go. All right, so now that's the thinking part. We just crunch numbers from now. 11 times 145 times 60 divided by 96,485 divided by 3 and times 52. So that's, let's see, three significant figures. 17.2 grams. Grams of chromium metal are deposited on that something. Let's say it's deposited on a bumper. Actually, you won't get a good, if you're going to chrome plate a bumper like for an antique car, you're not going to get a good lasting deposit of chromium directly on steel. It won't hold. So what they have to do is they plate, I think nickel first on the steel, which is very compatible with it. And then they plate copper on top of the nickel, which is compatible with the nickel. And then they plate chromium on top of the copper, which is compatible. And that'll hold. I used to have a banana seat bicycle with high handlebars that you could do tricks on stuff. And it had a chrome plated frame. Yeah. I was the cat's meow. Let's see. Okay. 72, short answer. All righty. We ought to be getting close to the end. Balance the following equation in acidic solution. Didn't we do this one already? That sure looks familiar. CR207, CR207, 2 minus, plus iodide ion yields CR3 plus iodate. Sure looks familiar. Okay, we've done this one before. That's 6 plus, that's -1, 3 plus. This is, let's see, plus 5. We did this one already. But I'll do it again just for posterity's sake. All right, oxidation stat and reduction stat. Oxidation, we're going to increase the oxidation number. We're going from -1 to +5. That's the oxidation step. +5. Okay. And this must be the reduction step. 07, 6 plus, and we're going to chromium 3 plus. Okay. So 1 iodine, 2 chromium. There we go. Now oxygens. We need 3 oxygens over here, 3 waters. And that's 6 hydrogens plus 6. Oops. There we go. Now on this side we have 7 waters. And over here we have 14 hydrogens. This is the reduction, so we're going to have electrons here. We have to add 3 for each chromium, but they're 2 chromiums, so that's 6 electrons. And this iodine goes from -1 to +6. That's 6 electrons, right? Maybe we didn't do this one before, because I don't remember one coming out exactly right. We did something else with this reaction. Okay. Just checking myself. Yeah, okay. Electrons are already balanced, right? So we can combine. Get rid of the electrons. 6 hydrogens out here leaves us with 8 here. And waters, 3 waters over there, they cancel and leave us with 4 here. So now if we add it together, and we put the chromium first, CR207, 2 minus, then 1 iodide, right? Then plus 8 hydrogens, yields 2 chromiums over here, and iodate, 1 iodate, plus whoa, 4 waters, yeah, thank you. Can't have hydrogens over there and no waters over here. Okay. So does that agree with our 4 waters? Yeah, that's it. Balanced equation. Right. Oh, we got another one. This one is basic solution. Okay. Now we're talking. I need a new marker. This one's starting to poop out on me. Went in my bag. $75. Okay, what are we starting with? Bismuth hydroxide. Plus SNO2, 2 minus. Stannate ion. Yields bismuth. I assume this is, would that be a metal? Bismuth. Yeah, that's a metal. Should be solid. It doesn't matter really. SNO3, 2 minus. SNO3, 2 minus. Okay. So oxidation and reduction. Okay. Let's see. Bismuth, that's the easy one. That's 0. This is 3 minuses, so this one has to be a 3 plus. Right? And this oxygen is going to be 2 minus, and this is a 1 plus. This one is -2 times 2 is -4. We got to hold 2 of them out, so we only have to balance that one. So that's a +2. And this one is -2 times 3 is -6. Hold 2 out. This one's a +4. There we go. Now we've got all of our oxidation numbers. We can tell which is which. Which one was oxidized? Bismuth was reduced. It went from 3 to 0. So 10 was oxidized. This one, right, with a +2 here, went to this one. Right. Yeah, that's right. With a +4. And then the reduction must be this one. Bismuth hydroxide. You know what? I wonder if it'd be more efficient to bust that up. Is bismuth hydroxide soluble? I don't know if it's in the list. Let me check it. Bismuth. No, it's not there. So I don't know if it's soluble or not. We'll have to leave it the way it is. If bismuth hydroxide is soluble, then we could write them as separate ions. Okay, so that one goes to this one. This is 3 plus. Okay. We got 110 and 110, that's good. We got 1 bismuth, that's good. Now let's balance the oxygens. We have 3 over here and 2 over there, so we need another one over here. And 2 hydrogens over here. Bet. Okay, we've got 3 oxygens over here. We need 3 oxygens over here. Okay. Now that gets us 6 hydrogens here, but we already got 3 hydrogens over here. So we only need 3 more hydrogens, right? Now let's do the electrons. Oxidation, we need electrons on this side. So we're going from +2, +4, that means 2 electrons, right? -2 and a +4 is +2. And then we have electrons on this side. We went from 3 plus to 0. That means we had to add 3 electrons for each bismuth. So far, so good. Now let's match the electrons. 3 and 2. 3, and 2. So that's going to be 3 here, 3 there, 6 there, 6 there, and 3 here. This will be 2 there, 6 there, 6 there, and 2 here, and 6 there. Okay. So yeah, I use that up. Okay. Now let's see if we can cancel some stuff. We got 6 waters here and 3 waters there. That water's gone, and this one goes back to 3. Electrons. Electrons cancel. 6 hydrogens here. 6 hydrogens there. Okay, now we can add them together, I think. So let's put them in the same order. 2 bismuth hydroxide. Plus 3 SNO2 2 minus. Okay. That canceled, that canceled. That canceled. Yields 2 bismuth and 3 SNO3 2 minus. And then we had 3 waters over here. Okay. So is this in basic solution? It's already in basic solution. Okay, so we don't have to do anything to it. What we did, we canceled this hydrogens with these hydrogens. So we didn't have to neutralize any hydrogens. We've already got hydroxyls here from the bismuth hydroxide. So this is in basic solution. We didn't have to do anything else, but just add them together. That's it. That's all I had marked. Did you want to look at any others? Probably not. We didn't do any shorthand notation. I thought I saw some in here. Let me see, why did I leave those out? We're too fast. I miss them. I saw at least one. There's one right there. What's the balanced chemical equation corresponding to the following cell diagram? The standard way, let me just work that one, right? 29. I don't know why I left that out. It should have been in there. I just need to know this shorthand notation. I think I went through it in the lecture. So if we write this, 29. If we write sodium, solid, then a line, and then sodium, aqueous, and then that's a salt bridge. This is a phase difference, solid to solution. We write a single line. A double line means a separation between the cells. It's either a salt bridge or a porous disc. We have copper, 2+ aqueous, and then copper metal. That's the way we wrote our cells. This is the cathode. And this is the anode by convention, which means what? Electrons are going to flow from this side to this side. And then the salt bridge is going to take care of the ionic balance. So if we were going to write the balanced equation, right, for the anode, we've got to lose electrons. Right? So sodium solid yields sodium plus 1 electron. And then for the cathode, we've got copper 2 plus 2 electrons yields copper metal. So that means this one has to be multiplied by 2. And that would be 2 Na solid plus copper 2 plus yields 2 Na plus an aqueous solution plus copper solid. That would be the balanced equation. Okay? That's how you interpret one of these abbreviated diagrams. If, let me think. Because sometimes you have an electrode that doesn't participate in the reaction, but you do have to include a phase. So if this were a platinum electrode, we would put PT solid in here with the phase difference. But then over on this side, you would have both aqueous elements together with no phase difference. Is that the only one I had in there? Oh, there's one. Oops, sorry, too far. Right there. That's the standard. When you write it, when you draw a cell diagram or you write it in shorthand, cathode's always on the right, anode's always on the left. Electrons flow from here around to there. Okay, I guess we're done then.